Good morning, students. Next, we discuss window and clipping. See here, different of the topics is there. First one is the clipping, line clipping, polygon clipping, normalized transformations, viewing transformations. Okay. See, clipping. So, clipping refers to the removal of the part of the scale. So, simply we can say which are the outside of the window. That lines or that polygons will be removed. It is called as a clipping. That way you can say clipping refers to the removal of parts of the scene. Okay, any procedure which identifies that portion of a picture which is either inside or outside a region is referred to as a clipping algorithm or clippings. Okay, so we have to identify any procedure which the portion of picture which is the either inside or outside of the clipping of the particular area, then it is referred as clipping algorithm or clippings. Okay, so the region against which an object is to be clipped is called as clipping window. So the clipping window is called which an object is to be clipped into the outside of the windows is called clipping window. So usually it is a rectangular in shape. Okay, so window is it is a selected area of the picture. So window is selected area of the particular picture. Okay, so for example, so this is a window. For example, take a triangle like this. Now we can remove this part of the area, that is the clipping of the outside of the window. Then we can get this is in this image. Okay, so in that way you can say it may be inside or outside. We can define the particular clipping values. We can remove the particular windows. Okay, so following are the graphic primitives that we are going to study the under clipping, that is a point clipping, line clipping and polygon clippings. So there are three type of clippings. First one is the point clipping, second one is the line clipping, and third one is the polygon clippings. Okay, based upon these we are now discussing the three type of the clippings. So point clipping, line clipping, polygon clipping. See, point clipping. So display p equal to x comma y if there are the four conditions, that is xw min less than or equal to x, xw max greater than or equal to x, yw min less than or equal to y, and yw max greater than or equal to y. So based upon these four conditions, we can identify which is the inside of the point, which is the point is inside of the window, which is the point is outside of the window. Okay. See, for example, this one. This is an example, that is x min, x max, y min, y max. See here, we can take the 2 points, that is the P1 and P2. Here, P2 is the inside of the window and P1 is the outside of the window. So now we can delete the P1 because of it is in outside of the window. What are the points, what are the lines, what are the polygons, whatever maybe outside of the window that lines are, we can clip it. There is a remove of the particular scene. In that way it is called as a clipping. Okay, so there are the four conditions. Based upon these four conditions we can identify which is the inside of the window, which is the outside of the window. That is xw min less than or equal to x, and x less than or equal to xw max, yw min less than or equal to y, and y less than or equal to yw max. Okay, see here, second example. Sorry, this is the P1, P2. P2 is the inside of the window, P1 is the outside of the window. Now we can delete the P1. So line clipping. So these are the line clipping. See, this is the P1, P2 inside of the window, P1 dash, P7 dash is inside of the window, P1 dash 5, P6 is the inside of the window. See, before going that, see, we check P1, P2 inside of the window, P6, P5 some part of the outside of the window, some part of the inside of the window, P4, P3 completely outside of the window, P7, P8 so some part of the outside of the window, some part of the inside of the window, then P10, P9, P10 completely outside of the window. When we apply the line clipping algorithms, then we can get this one. So P1, P2, P6, Py dash, P7 dash, P8 dash, because we can, whenever we are clipping that, first of all we identify which is the intersect point of the particular line. So based on that intersect point of the line, we can remove the outside of this lines particular scene. Okay, so mainly it will depend upon the intersect point of the lines. So based upon that intersect point of the lines, we can remove the outside of the window lines. Okay, the particular given objects. See, so this is the row and column wise x min, x max, y min, y max. So based upon that, we can remove the lines. Okay, see here, it will be completely outside of the window. It will be completely outside of the window, completely inside of the window. But here some part of inside and some part of outside. Here also some part of inside, some part outside. Here also some part of complete outside of the window. Okay, so now we can calculate all the points. Based upon that, we can calculate which are the inside and which are the outsides. So based upon the conditions. So main is the first one algorithm is Cohen-Sutherland line clipping algorithm. Based on that, we can remove the lines. See, space is divided into the regions based on the window boundaries. Each region has unique 4-bit region code. Region code indicates the position of the regions with respect to the window, that is left, right, below, above. So here, based upon that, that is the L or B, sorry, A, B or L, that is above, below, right, left, or TBRL, that is the top, below, right, left. Based upon that, we can define the values, that is 1001 on top of the left corner, middle top 1000, top right 1010, middle left 001, middle window 4 zeros, middle right 0010, next bottom left 0101, below 0100, right 0110. So now we calculate all, when all the points are the zero, it is the inside of the window, remaining all the outside of the windows. Okay, so based on these region code, we can calculate which is the inside of the window and which line is the outside of the window, or which point, okay, line. Okay, based upon that, we can calculate. It will be defined the Cohen-Sutherland's. Okay, so mainly based upon the TBRL or ABRL, that is above, below, right, left, or top, below, right, left. See, this is the codes x maximum y, see, x minimum y minimum. This is x minimum y minimum. This is the x maximum y maximum. This is the x minimum, sorry, x maximum y minimum, x minimum y maximum. Okay, likewise we can define the region codes. See, bit 0, that is x less than x minimum, bit 1 x greater than x maximum, bit 2 y less than y minimum, bit 3 y greater than y maximum. Based on these conditions, we can find which is the inside and which is the outside of the lines. So x less than x minimum, x greater than x maximum, y less than y minimum, y greater than y maximum. See, every endpoint of the line is labeled with the appropriate region code. There are three cases. First one, lines inside of the window cannot be clipped. Case 2, line outside the window. Take end operation the outcodes of the endpoints of the line. If answer of end operation is non-zero, means line is outside of the window and hence discard the particular lines. Case 3, lines are partially inside the window. That is lines for which the end operation of the end coordinates is 0. These are identified as a partially visible lines. Okay, here there are three cases already discussed. First one is all are the inside. Second one is the completely outside. And third one is the some part of the line is inside and some part of the outside of the window. But go from the point, it may be inside, it may be outside, not partial. But when go for the line, it may be some part of the may be completely inside or part of the complete outside, or maybe some partial, that is some part of the inside and some part of the outside. So in completely inside we cannot calculate, complete outside can, but it may be partial. In that way we can identify which is the all zeros, which are the non-zeros, which are the non-zeros, that part of the lines will be deleted and remain will be assigned. See, these lines are processed as follows. Find the intersection of those lines with the edges of window. We can use the region code to determine which window boundaries should be considered for intersection. That is region code 10000, then the line intersect with the top boundary. So now find the intersection of that boundary only. So check other the end of the line to get other intersections. So based upon the intersection points, we can identify which is the inside, which is outside, based upon the boundaries also. So draw the lines between calculated intersections. So intersections are calculated as y coordinates of intersection point with a vertical boundary can be calculated as y equal to y1 plus m into x minus x1, x equal to x minimum or x maximum, and m equal to y2 minus y1 by x2 minus x, that is the delta y by delta x. X coordinates of the intersection points with the horizontal boundary can be calculated as x equal to x1 plus y minus y1 by m, y equal to y min or y max, and m equal to y2 minus y1 by x2 minus x1. So read two endpoints of the line, say P1 of x1 comma y1 and P2 of x2 comma y2. Read two corners of window left top and right bottom, say wx1 comma wy1 and wx2 comma wy2. So assign the region codes of the two end coordinate points of P1, that is x less than x w min, x greater than x w max, y less than y w min, y greater than y w max. Based upon these conditions, we can identify which is the inside, which is the outside, and which are part of the clipping or which are part of the not clippings. Okay, so apply the visibility check on the lines. So if line is partially visible, then if region codes for the both endpoints are non-zero, find intersection points P1 and P2 with boundary edges by checking the region codes. If region codes for any one endpoint is non-zero, then find intersection point P1 or P2 with the boundary edges. Divide the line segment considering the intersection points, draw the line segment and stop the particular process. Next, polygon clipping. So edges of polygons need to be tested against clipping rectangle, may need to add new edges. Edges are discarded or divided. Multiple polygons can be result from a single polygon. Okay, see, this is the polygon, but here this is the window. Now we can remove outside of the window polygon, that is this all, or we can remove. Okay, then we can get like this. Take this one. Now we can get clip the all the outside of the window polygons. Now we can get this one. Okay, so each edges of polygon need to be tested against the clipping rectangles. Okay, may need to add the new edge. Edges discarded or divided. Multiple polygons can be result from a single polygons. In polygon, that is the Sutherland-Hodgman polygon clipping. See, a technique for clipping areas developed by Sutherland and Hodgman. In line drawing algorithm, Sutherland, Cohen-Sutherland, but here Sutherland Hodgman. So put simply, the polygon is clipped by comparing it against each boundary in turns. See here. So this is the original area. When we can clip left, right. So here we can define the different area. There is a left part of the, first of all we can remove left part. Then next we can remove right part. Then next we can remove bottom part. Then next we can remove top part. Then we can get the inside of the window boundaries. See here. This is the clipping area. Now first we can remove this part, that is it will be left side. Next, then clip left. Next, clip right. Now we can remove this one. Next, clip bottom or whatever top. Okay, now clip top. Next, clip the bottom. Finally we can get the image. So In Hodgman algorithm, so we can take the four areas, there is four regions, but in line clipping we can take 9 regions codes, but here take only four areas, that is left, right, top, bottom. So first we can remove the left side of the outside of the window. Next remove the right side of the window. Next remove the bottom of the window. Next remove the top of the window. Okay. C. Input output for algorithm. Input list of polygon vertices in order. Output list of clipped polygon vertices consisting of old vertices and new vertices. In Sutherland Hodgman does 4 tests on every edge of the polygon. Inside, outside, outside, inside. There is 1, 1, 1, 0, 0, 0, 0, 1. So output coordinate list is created by doing these tests on every edge of the polygons. C. Edge from S to P takes one of the four cases. C. Inside we can save P, that is 4 cases. Completely inside we can take P value, that is S to P. Second one, some part of inside and some part of outside we can take intersect point, that is S dash. Here we can take I, whatever maybe. We can take the one, save intersect point. Next, complete outside point. We cannot save anything. Some part of outside and some part of the inside we can save intersect point and inside of the point. Okay, so mainly we can take these four cases. First one is completely outside. Second one is inside to outside. Third one is outside inside. Fourth one is inside outside. Okay, so completely inside, completely outside, inside outside, outside inside. So for based on these four we can calculate all the lines, and we can remove the outside of the window lines, okay, based upon the Sutherland and Hodgman clippings. So these are the main four operations, that is completely inside, inside outside, completely outside, outside inside. With inside outside take p value, that is the next end of the value. Inside outside intersect point, outside not saving, outside inside take intersect point and inside of the point. Okay, that is C. S inside plane and P inside plane save P in the outside list. S inside plane and P outside plane find intersection point I, save I in the output list. S outside plane and P outside plane save nothing. S outside plane and P inside plane find intersection point I, save I in the output list followed by P. So read polygon vertices, read window coordinates for every edge of window do. Check every edge of the polygon to do 4 tests. Save the resultant vertices and the intersection in the output list. The resultant set of vertices is then sent for checking against the next boundary. Draw polygon using output list and stop the process. So we have generating generalized clippings. We have used 4 clipping routines, one for each boundary, but these routines are identical. They different only in their test for determining whether a point is inside or outside of the boundary. Okay, it is possible to write one single routine and pass information about boundary as parameters. So this change allows to clip along any line, that is not just for the horizontal or vertical boundaries. So such general routine can be used to clip along an arbitrary convex polygons. That is a window with 6 clipping boundaries, 1, 2, 3, 4, 5, 6. Okay. So 1, 2, 3, 4, 5, 6. Okay. So 6 clipping boundaries. So next, normalized coordinates. So different display devices have different screen sizes and resolutions, which is measured in pixels. Picture on a screen with high resolution appears small in size, whereas same pic on screen with less resolution appears on big in size. So to avoid this, we make our program devices independent. So picture coordinates have to be represented in some units other than pixels. Okay, so device independent units are called as a normalized device coordinates. So that is the device independence units. What are the device independence there? That is called as the normalized device coordinates. Okay, in the screen measures 1 unit wide and 1 unit length. Okay, so we are using the different type of the display devices on the different screens of the sizes based upon the particular conditions. We can define the high resolution appear in the scene that it will be perfectly. We can assign the image of the particular screens. Okay, so in this screen measures 1 unit wide and 1 unit of the length based upon the particular coordinate values. C. So transformation to normalized coordinates. So interpreter is used to convert normalized coordinates into device coordinates. A simple linear formula is used for this. X equal to xn into xw, y equal to yn into yw, where x equal to actual device for x coordinate, y equal to actual device for y coordinate, xn equal to normalized x coordinate, yn equal to normalized y coordinate, xw equal to width of actual screen in pixels, yw equal to height of actual screen in pixels. Okay, so based upon the interpreter we can convert normalized coordinates into the device coordinates. Okay, so we are using the different about the equations, that is xn into xw, yn into yw. Okay, next, viewing transformation. So an image is defined in a word coordinate system, the WSCS, that is using Cartesian coordinate systems. So word coordinate system is application specific. Okay, for example, drawing dimensions may be in meters, kilometers, feet. Okay, when picture is represented on display device, it is measured in physical device coordinate system, that is PDCS, corresponding to the display device. So viewing transformations, mapping of coordinates is achieved with the use of coordinate transformation, that is maps pictures coordinates in the WCS to display the coordinates in the PDCS. So WCS is infinite in extent and device display area is finite. A word coordinate area selected for display is called a window. Define the what to display. An area on device to which a window is mapped is called view report. Okay, this is the view report. See, this is the clipping window. Then we can delete the complete outside of the window. Then this is the viewing report. Okay, in that way, XW min window, XW max, YW min, YW max, and go for the view report, that is XV min, XV max, YV min, YV max. Okay, so an area on a device to which a window is mapped is called viewport. Okay, so the window to viewport coordinate transformation is, would you like to specify a drawing in the word coordinates, display in screen coordinates. So need some sort of mappings called window to viewport mappings. So basic W to view V, that is window to view mapping steps: define a word window, define a viewport, compute a mapping from window to viewport. Okay. C is showing the mappings of the object from window to viewpoint. A point at xw, yw in window is mapped into position xv, yv in the associated viewport. See here, xw, yw. This is the report view report of the position xv, yv. Okay, so a point at xw, yw in the window is mapped into the position of xv, yv in the associated view reports. Okay. See, to maintain the relative replacement in viewport as in window view required xv minus xv min by xv max minus xv min equal to xw minus xw min by xw max xw min. Okay, so likewise yv minus yv min by yv max minus yv min, yw minus yw min by yw max minus yw min. Solving these equations for view positions, xv equal to xv min plus w minus w min sx, yv equal to yv min plus yw minus yw min of s5. Scaling factor sx equal to xv max minus xv min by xw max minus xw min, s5 equal to yv max minus yv min by yw max minus yw min. Okay. So mapping of window to viewpoint required following transformation: scaling using fixed point position w min that scales the window area to size of the view report. In translation, translating the scaled window area to the position of the view report. So from the workstation of transformation of object description from normalized coordinates to device coordinates, it is accomplished by selecting a window area in normalized space and viewport area in coordinates of display devices. So likewise, so this is an object, translation, scaling, and translate. Okay, already we have discussed the pivot element of the particular changing of the pivot clipping. So same as like that. Okay, into to viewport coordinate of the transformations. So w t dot s t into s into t inverse equal to 100,010 xw minus xw min minus yw min 1 s equal to sx000 sy00001, that is t inverse equal to 100,010 xw min yw min 1. This is the modeling view of the transformation. So consider the word coordinate values. Word 2 viewing coordinates, projection transformation, transformation projections, and map normalized coordinates and devise the coordinates. Thank you.